In this session, we will talk about artificial neural networks. In this session, we will talk about the following learning outcomes. You should be able to outline the fundamental principles of artificial neural networks and the underlying biological motivation. You should be able to demonstrate the usage of a perceptron and reproduce the characteristics of a multi-layer network and how learning could possibly be implemented. And you should be able to explain and discuss different publications in healthcare which make use of artificial neural networks. Artificial neural networks in medicine have been applied in different areas such as image analysis, drug design, diagnostic systems, or biochemical analysis. The following advantages can be associated with neural networks for predicting medical outcomes. They require less formal statistical training to develop. They can implicitly detect complex nonlinear relationships between independent and dependent variables. They are able to detect all possible interactions between predictor variables, and they can be developed using multiple different training algorithms. What are the disadvantages of using neural networks for predicting medical outcomes? Firstly, it's a black box algorithm. All the knowledge is stored in the weights of the individual trained neural network. It's very hard to achieve a feature ranking based on the weights. For that reason, it's very hard to identify a specific interpretation why a neural network came up with a specific solution. Training a neural network requires a huge amount of computational resources. For example, it might take a very long time because of the different degrees of freedom in terms of activation functions, number of neurons per hidden layer, and number of hidden layers. It's prone to overfitting. Presenting data too often to a neural network might overtrain on the existing data, and it might predict very poorly on unseen test data sets. Most model development is empirically, and many methodological issues still remain to be resolved. Despite of that, there are many successful applications of artificial neural networks. This individual list here is not exhaustive, but these are just some examples how an artificial neural network could possibly be used for diagnosis or for detection of disease-free survival or prediction of seizures and so on. How would you process features from healthcare and medicine in an artificial neural network? For that, you have some homework to do. You will find some references and you should read these papers and you should familiarize yourself with the different architecture. This is important if you want to construct your own artificial neural network for a specific clinical problem. How would you use a neural network for a real-world example? In this slide, you can see a screenshot of a tool that can be used for diagnosis and treatment planning for prostate cancer. A dataset was used from previous patients attending this hospital. The artificial neural network was trained based on this real-world dataset. Now the artificial neural network can be used to predict for new patients whether these patients would need a biopsy or not. Interestingly, this data-driven approach is far more flexible than a rigid approach based on a clinical guideline where a specific threshold has to be satisfied in order to do a biopsy or not. If you want to use this tool, check out the provided link. If you want to understand more the historical context and how artificial neurons were developed, check out this historical landmark paper from 1943. McCulloch already developed the key principles of an artificial neuron in 1943. In this slide, you can see the key principles of a McCulloch-Pitts neuron. That concept was already developed in 1943. It shows the three key components of an artificial neuron. Firstly, we have a set of weighted inputs called weights. Secondly, we have an adder function that sums up the input signals That is the equivalent to the membrane of the biological cell that collects an electrical charge. So essentially that is the weighted average of the input, ranging from x1 to xm. And then we have an activation function. So the output of our weighted average will be put into an activation function. The activation function decides whether a neuron fires or not. In that simple example, you can see a threshold function. If a specific threshold is satisfied, for example theta, and your output is larger than your threshold, then your neuron would fire and the output would be 1. Otherwise, it wouldn't fire and the output would be 0. That specific activation function can also be changed. However, the weighted average, the adder function, wouldn't be changed. On this slide, you can see some activation functions. An activation function is a hyperparameter for your artificial neural network. The sigmoid function is, for example, an activation function that is widely used. Consider you have an artificial neuron and you want to implement learning. The first thing that you need is a quantitative measurement to assess how far away are you from your target. Consider you have that. You have an error, and that error can be measured, for example, in a quantitative measurement. So the key principle is you update your weights, and in the next iteration, hopefully your error rate decreased because your artificial neuron can better predict what it needs to predict. In 1958, Frank Rosenblatt invented a new algorithm called the Perceptron Algorithm. The Perceptron Algorithm is a very simple algorithm that helps that a neuron can learn specific problems which are linear separable. The Perceptron Algorithm was also implemented in hardware. The Perceptron Algorithm has 3 components. Firstly, you need to initialize your neural network. Normally, you do this with small positive and negative random numbers. Secondly, in your training phase, you use for each input vector the activation function, and you run this through the activation function. Then you have your output y. Once you have that, you can compare your output to your target, and you use a learning rate called eta. You use the difference between your target and your output times eta times your input, and you subtract this from the previous weight, and that defines the new weight. If you do this for a couple of iterations, your neural network will converge if it's a linear separable problem. How do you use the neural network for recall? Recall is quite simple. For each neuron, you just pass the output of your weighted sum through the activation function, and that is your prediction. In this slide, you can see on the left-hand side a linear separable problem. One neuron with 2 input features can be adapted in a way that it can be resembled by a hyperplane in your feature space, and there will be a hyperplane or a set of weights which perfectly separates your red circles from the blue crosses. If you have a nonlinear separable problem in the center of this slide and on the right-hand side, you wouldn't be able to find a set of weights which perfectly separates these 2 instances. So that nonlinear separable problem cannot be solved with simply one neuron. So the perceptron algorithm, you can see here how the perceptron algorithm would possibly work. So you have a small set of random numbers, and this here is the OR function, and it should learn the OR. This slide shows you a worked out example of 2 iterations how the perceptron algorithm would learn the OR function. The OR function basically has an output 1 or true always if at least one input is also 1. Consider you have small random numbers W0, W1, W2, these are your weights, and normally these would be random numbers. You have a bias term -1. You could consider this as an additional feature with a fixed value of -1, and you would have a learning rate in this example of 0.25. How would you calculate the first weight updates? If you take the input of 0, 0, if you look in the table, the output should be 0, so your output neuron should not fire. However, if you look at the individual set of weights, your output neuron would fire. So obviously this is wrong and we need to adjust the weights. If we use the previous equation, and if you look at the first update for W1, for your bias term with your learning rate 0.25, you will get a new weight 0.2. You do the same thing for W1 and W2, except you wouldn't use the bias term, you use the input 0, 0. In your second iteration, you take another instance from your training set. You have the same problem, your neuron does not fire, but it should fire. If you have an input of 0, 1, if you look in the table, your neuron, your output neuron should fire, so the output should be 1. So you update W0, W1, W2, and these are the new weights. And then you would do the same thing in this third iteration, and so on. And at one point, because the OR function is a linear separable problem, the perceptron algorithm would converge and would find a set of weights which perfectly fits your prediction. If you want to learn complex functions, it's not enough just to use one neuron. What you need is a complicated multi-layer perceptron, a combination of many neurons and many hidden layers. Your information flow is unidirectional. Data or features are presented to your input layer, to your input neurons, and this information is passed on to the hidden layer. The output of your hidden layer is passed on to the output layer. One neuron's output is another neuron's input. This slide shows a formal description of the multilayer network. Firstly, you present your data to your input layer. Once you've done this, you pass the information from your input layer to the hidden layer and from the hidden layer to the output layer. If you have another hidden layer, you can also adjust the multilayer network by adding more hidden layers. You also have weights. Each edge in this picture has a weight, W. How would you possibly store this in a programming language? For example, in a matrix, you can store all the individual weights. And you can also save the weights once you think your multilayer network is trained. Your output Y can also be used to calculate an error rate, because based on your training set you would know how far away you are from your target. How would you learn in this multilayer network? One technique is called the backpropagation algorithm. You have a feed-forward process in your multilayer network, you calculate the error rate, and then you backpropagate the error through the multilayer network, and you adjust the weights. And then you do this again. It's called backpropagation algorithm because you backpropagate the original error rate and update continuously the individual weights. If you present your data too often to your artificial neural network, it will overfit on your training set. How would you possibly detect that? So your error rate normally would go down in your training set with every iteration, but your error rate for a validation set, a data set your artificial neural network has not seen before, would at one point increase. And at this point, you could argue that your artificial neural network is already starting to overfit on your data. So as a conclusion, we talked about the following learning outcomes. We talked about the fundamental principles of an artificial neural network and the underlying biological motivation. We demonstrated the usage of a perceptron algorithm, and you saw a couple of computational examples for the perceptron algorithm. We also looked at the characteristics of a multilayer network and how learning could possibly be implemented with a backpropagation algorithm. You have more material to read online and to discuss different publications in healthcare which make use of artificial neural networks.